Hello class 12. In this video we are going to talk about astronomical telescopes. We are going to discuss about astronomical telescopes. Okay, so astronomical telescopes can be basically of two kinds. One is called the refracting type and the other is something called the reflecting type astronomical telescope. So first of all we are going to discuss about the refracting type astronomical telescope. Okay, so this is the basic picture for astronomical telescopes, refracting type, wherein we have two lenses, the objective lens and the eyepiece. In case of refracting type telescope, what happens is, or rather the difference of refracting type telescopes when compared to compound microscopes is that in case of compound microscopes, we had the objective lens which had a shorter focal length as compared to the eyepiece. The eyepiece had a longer focal length in case of the compound microscope. In case of refracting type telescopes, it's just the opposite. The objective has a longer focal length. So you can see f0 written over here. So that is the focal point or principal focus of your objective. So OA dash is, so to say, the focal length of your objective. And you can see FE written over here. FE is the focal point or principal focus, that of your eyepiece. So to say, this distance EFE is the focal length of your eyepiece. So we can see from the picture itself that the objective has a longer focal length than your eyepiece. Okay. So in what telescopes, they do is that you have the object AB, like stars and planets, okay, very big objects, but at infinity, very, very far away from the telescope, from the eye, so to say. So in order to get a clear image, we need to have an objective lens which can collect as much light coming from your object, as possible. So to say, the objective has to be big. The objective lens has to be a big lens, or so to say, technically speaking, it has to have a large aperture. Aperture is the distance, you can say, is the distance between the two ends, okay, two ends of the lens. So we need to have an objective having a large aperture which can collect as much light as possible coming from our object. So since the object is at infinity, we have two parallel rays of light coming and hitting the objective. Now these rays of light are converged by our objective at this point A dash, and thereby A dash B dash is the real image of our object at infinity formed. Now this image A dash B dash is formed at the focal point of our objective lens. Since the object is at infinity, so the image has to be formed at the focal point. So A dash B dash is the real image formed by our objective at its focal point f0. Now it is this image A dash B dash, which is formed at the focal point of the objective, lies in between the optical center E and the focal point of our eyepiece. The distance between the objective and the eyepiece is so adjusted. Okay, the telescope will have some knobs, precisely called rack and pinion arrangement. Okay, so by using those knobs, the distance between the objective and the eyepiece is so adjusted that this image A dash B dash is formed in between the optical center and focal point of our eyepiece. So since this A dash B dash is formed in between the optical center and focal point of the eyepiece, so we get to see a virtual image A double dash B double dash formed by the eyepiece. Okay, so this is the final image A double dash B double dash, which is formed, that of our object AB at infinity, and this is what we get to see. Okay, so UE is the object distance, you can see, and FE is the focal length of the eyepiece. VE is the distance, or rather the image distance. Now we need to calculate the magnifying power. Magnifying power M, from definition or by definition, we know it is the ratio of angle subtended by image at the eye, which you see is beta over here. So A double dash B double dash, which is our final image, is subtending an angle beta at the eyepiece or at the eye, since the eye and the eyepiece are very close to each other. So beta is the angle formed by the final image at the eyepiece or at the eye. So divided by angle subtended by object at the eye. So the object AB is at infinity. So we have parallel rays of light coming. So the angle subtended by the object at the eye is alpha. Now actually alpha is the angle subtended at the objective, but this distance, or rather the distance between the eye and the objective, is negligible compared to the distance between the telescope and our object AB. So therefore we consider alpha to be the angle subtended by the object at the eye itself. So since beta, alpha are very small angles, okay, the mathematics here is the same. So m is beta by alpha, which is almost equal to tan beta by tan alpha. Since beta and alpha are very small angles, so instead of beta we write tan beta, instead of alpha tan alpha. All right. Now what is tan beta? Tan beta over here, you can see, is a dash b dash, the perpendicular, divided by the base a dash e. So a dash b dash divided by a dash e divided by, now since this angle is alpha, its vertically opposite angle will also be alpha. So this angle is also alpha. So from this right angle triangle O B dash A dash, we can write tan alpha is the perpendicular A dash B dash divided by the base O A dash. So or A O dash. So that is what we have here. So A dash B dash, they divide each other, and we are only left with A dash O divided by A dash E. Now what is A dash O? A dash O, like we've already mentioned before, is the focal length of your objective. So f naught is the focal length of the objective divided by, and by the way, the focal length of the objective, this O A dash or A dash O f naught is positive, since it is on the right hand side of the optical center for the objective. So we are also incorporating sign convention. So f naught is positive. And what is A dash E? A dash E is this distance. This is the distance or object distance measured from the eyepiece. Now since it is on the left hand side of the optical center for the eyepiece, so it is negative. And thereby we have the magnifying power of a refracting type telescope is minus f naught divided by UE. So this is our equation number 1. This is the general expression for the magnifying power of a refracting type telescope. Now we of course are to deal with two cases. Case 1, when the image A double dash B double dash is formed at D. So to say, when this image A double dash B double dash is formed at distance D from the eyepiece or from the eye. Precisely, it is actually from the eye. Okay, so we have the lens formula. Now for the eyepiece, V, which we have denoted by VE, here you can see in the picture VE. So this VE is equal to minus D, since it is on the left hand side of the optical center for the eyepiece. So V, which is VE, is minus D. Likewise U is minus UE, and the focal length of the eyepiece is positive. The focal length of the eyepiece, always there are two focal points for any lens. Remember, this is the first focal point, this is the second focal point. Focal length is always the distance of the second focal point from the optical center, mind you. So therefore it is always taken to be positive. All right, so we have the focal length to be positive. So substituting these values, we have 1 by minus D minus 1 by minus UE is equal to 1 by FE. Rearranging, please check the mathematics. So 1 by UE is this much, and we've taken out 1 by FE common from here. So we are left with 1 plus FE by D. Now what we do is, this is the value of 1 by UE. Now the value of this value of 1 by UE, we substitute in equation number 1 here. So 1 by UE. So what we get is the magnifying power is minus f naught by FE into 1 plus FE by D. This is the value of the magnifying power of the refracting telescope when the image is formed at least distance of distinct vision. All right. Now the second case is when the final image A double dash B double dash is formed at infinity. Now in this case, what is more important is you drawing the picture properly. Okay, so this is the picture like. So the object is AB. We have parallel rays of light coming and hitting the objective, which has a shorter focal length, mind you. Now this image, the real image, is formed by the objective again, the same thing at its focus f0. This is the real image formed. Now for the final image A double dash B double dash to be formed at infinity, this A dash B dash should lie or should form at the focal point of the eyepiece also. So to say, for the final image A double dash B double dash to be formed at infinity, the focal length, the focal point of the objective and the focal point of the eyepiece should coincide. Okay, so only in that case we have the image formed at infinity. So for A double dash B double dash to be formed at infinity, the object distance from the eyepiece UE should be equal to its focal length itself, FE. And thereby, using this case in equation number 1, so UE is equal to FE, so we have magnifying power is minus F0 by FE. So that is the value of magnifying power, here you can see, when the image is formed at infinity. So this is all about the refracting type telescope. Now there is another kind of telescope, which is the reflecting type telescope. Now for reflecting type telescope, you only need to learn to draw the picture of the image formed by a reflecting type telescope. Previous years also, not in case of the reduced syllabus also, only you had to learn the formation of image by a reflecting type telescope. You have to learn to draw the picture. So we have the object AB at infinity here. So we have parallel rays of light coming. Now in case of reflecting type telescope, the objective is not a lens, but it is a mirror. And this is a concave mirror, M1. So we have parallel rays of light coming and hitting the concave mirror M1. So rays of light, they converge. Since concave mirrors, they converge rays of light. So they converge and we have a plane mirror M2 over here. Now this plane mirror also reflects the rays of light and we have the eyepiece finally. We have the eyepiece and this eyepiece focuses the rays of light at the eye. So what we get to see is, in case of reflecting type telescope, the final image is formed at infinity here. So this is the final image A double dash B double dash formed over here. So you all need to learn to draw this picture, remember. So rays of light coming, hitting the mirror, the concave mirror first of all. Concave mirror focuses the light or converges the light, rays of light at a plane mirror, and what happens is the plane mirror forms an image A dash B dash here, real image. Okay, now this A dash B dash is what is acting like the object for the eyepiece, remember. So we have a parallel ray of light coming here, parallel to the principal axis. Okay, and finally the image of A dash B dash is formed at infinity, A double dash B double dash. So you all need to learn to draw this picture for reflecting type telescope and learn the expression for reflecting type telescope. Okay, it is the same as in the case of your refracting type telescope. Refracting type telescope when the image is formed at infinity. Now the other thing that you get for reflecting type telescope is reflecting type telescope has certain advantages when compared to a refracting type telescope. At the most you'll be asked about 2 advantages of reflecting type telescope. I have given 3 over here. We are discussing 3. First is the image formed by reflecting type telescope is brighter than the image formed by a refracting type telescope. Now in case of refracting type telescope, what happens is the intensity of light is lost due to absorption by the lenses. Okay, the lenses, they observe some light also, or they reflect some amount of, not just refraction happens, mostly refraction is happening, but some amount of absorption of light and reflection of light also takes place from the lenses. So eventually what happens is the intensity of light coming from the image, image gets, not very bright, it gets dim. So therefore, the image coming from reflecting type telescope is brighter than the image formed by refracting type telescope. You just have to write the reasons. And in reflecting type telescope, the image is free from chromatic aberration. Now, what is chromatic aberration? In case of a lens, you have a lens. We have light of different colors, red light, blue light coming, say this is red light, then you have blue light coming. Now for different colors of light, the refractive index of a certain material will be different. So ideally what should have happened is all these different colors of light should have been focused at the same point. But because of chromatic aberration, what happens is for different colors of light, the refractive index being different, the focal length will also be different for the given lens. So what happens is these rays of light, they do not meet or they do not converge at the same point. So this is what is called chromatic aberration. Now, refracting telescopes will have chromatic aberration, but reflecting type telescopes, they are free from chromatic aberrations. And finally, like I told you before, the objective of telescope should have a large aperture to collect as much light coming from the far or distant object. So the image formed by lenses having such large aperture is distorted. What happens is the image formed by lenses having large apertures, they are distorted. But since reflecting type telescopes, there is no objective lens, what happens is the image formed by mirror, large mirrors are not distorted, and hence reflecting type telescope is free from such kind of distortion. So if you're asked at the most, like I said, for 2 marks, you will be asked 2 advantages of reflecting type telescopes. You can give any of your choice, or you can also refer the book for the advantages of reflecting type telescopes. Thank you.